So thanks for coming, everybody. Today's speaker is, sorry, I'm not used to speaking into a microphone. Shantanu Jathar. He joined the mechanical engineering department as an assistant professor at Colorado State University. His PhD is from Carnegie Mellon University, where he used numerical models and laboratory experiments to understand the atmospheric formation of organic aerosols from combustion sources such as cars, trucks, aircraft, and wildfires. He worked as a postdoctoral scholar at the University of California, Davis, where he was funded by the California Air Resources Board to improve the treatment of particulate matter in air quality models used for regulatory purposes. His research interests lie at the intersection of energy and the environment. By leveraging laboratory experiments and regional and global air quality models, he intends to study the atmospheric evolution and properties of air pollutants arising from energy systems, all in the interest of addressing future energy and environmental policy. Okay, so take it away.
Okay. Thanks, John. Thanks, Alma and John both for inviting me over and giving me this opportunity to show some of the work that me and my group have been doing at Colorado State University for the past 12 or 15 months. Clearly, there's a lot of people to thank here. The ones in red are my group at Colorado State. The ones in blue are Delphine Farmer's group at CSU in chemistry, and I've worked with Delphine closely over the past year. Some of the instruments that I've stolen air quality models from and instruments from without them knowing, but having acknowledged them in the as co-authors, and then some folks at EPA and some of the folks at atmospheric sciences at CSU. And I'm going to talk about both primary and secondary pollutants that arise from particularly diesel mobile sources, and an investigation through both measurements and modeling exercises. So Alma mentioned that I shouldn't spend too much time on an introduction, but I thought I'd share some fun facts about mobile sources and diesel sources particularly. So here's a figure from EPA's the status of our nation's air from 2015 that shows where these criteria pollutants and some air toxics come from in terms of their sources. And what I've highlighted is the contribution from both on and off-road mobile sources. So they're about 65 to 60% of carbon monoxide and NOx, about 30% of VOCs, very little SOx, and that's mostly because of very strict standards on the sulfur content in fuels, and about 20% of PM or particulate matter emissions. Bear in mind that these are primary emissions and don't consider a secondary component. And if you think about these sort of numbers, which are a million tons of these species, even if a small fraction of these small fraction of this NOx or VOC emissions translates into secondary PM production, you could get a doubling or a tripling of particulate matter, and therefore a much larger contribution from mobile sources. Diesels are about 30% of the mobile fleet in the United States. Globally, they're a lot more larger. About half of all mobile source engines are diesel engines. But despite the fact that they're only 30% of the mobile sources, they account for about 3/4 of the NOx and PM emissions. So mobile sources are important, and diesel engines are important too. And I thought I'd show this picture from New Delhi about a week ago, where concentrations of PM reached about 1,000 micrograms per cubic meter, and everyone decided to live life as they usually do, and you have these sort of poor kids running a 10K race, and clearly I just hope they made it through to the end. So as I mentioned in the last slide, diesel sources could also be a potentially large source of secondary pollutants, that is those formed in the atmosphere. But there are large uncertainties and unknowns surrounding the influence of engine loads, particularly low activity modes, that is idle conditions or low catalyst temperatures. Alternative fuels, so biofuels, there's a strong movement globally for wider adoption of fuels from biomass. For reasons that stem from environmental sustainability to energy independence, and also emissions controls that have been tacked on to diesel engines to reduce pollutant emissions of NOx and PM. And so here's a snapshot of the sort of the theme for today's seminar, which is all these types of applications in which diesel engines are used, produce particulate emissions, produce both organic and inorganic emissions that can be photochemically processed in the atmosphere, that can form more secondary PM, but can also form oxygenated VOCs and various types of reactive nitrogen species. So I timed myself, and I apologize if I tried to fool you in my abstract, but I won't be able to cover everything that I mentioned in the abstract. But I'm going to focus on 3 different studies that we've done over the past year. One is looking at photochemical production of SOA from diesel exhaust, where we varied a bunch of upstream conditions, and this has relevance because it tells us something about the atmospheric formation of SOA. We've looked at both the emissions and the photochemical production of this compound called isocyanic acid from modern day diesels, thinking about new pollutants of concern from diesel engine systems. And then a modeling study where we tried to resolve the ambient organic aerosol from a source and a precursor perspective. And this sort of will highlight the importance of mobile sources on urban air pollution. So the first study was motivated by the fact that environmental chamber studies that are typically used to study secondary organic aerosol formation are limited in a few different ways. One is that you can only simulate a few hours of photochemistry, and then the second is that chamber walls can affect the formation and the evolution of secondary organic aerosol in these experiments. So here is a study where we measured primary organic aerosol and secondary organic aerosol after a few hours of photochemistry, and you can see that even after a few hours of photochemistry, the SOA was as large as the POA component, or the primary organic aerosol component. But this is only after a few hours of photochemistry. There's also growing concern, as I mentioned, about low activity modes or idle conditions, or conditions where the diesel engines don't operate as designed, the use of biofuels, and how aftertreatment essentially perturbs the SOA production. And the problem, one of the reasons for this uncertainty is because studies that have focused on these 3 different things have been done across different engine and vehicle configurations. So it's been hard to systematically control the engine for all the other variables, and usually you run into issues of statistical power. So the goal of our study was to produce secondary organic aerosol from diesel exhaust using an oxidation flow reactor instead of a chamber, and look at the role of engine load, fuel, and aftertreatment. So an OFR is a small flow-through device, a cylindrical vessel about 13 liters or so. The advantages with that is you can simulate much longer time periods when compared to a chamber. And the other advantage is that because the residence times are so short, you are immune from effects from the wall. In our study, we used a tier 3, which would be something that would be sold in the United States prior to 2007, which is a research non-road diesel engine. It's heavily instrumented, so we can measure more than 30 variables associated with the engine in terms of the everything from the pressure inside the engine cylinder right up to the temperature on the exhaust. The nice thing with that is that we can run straight biodiesel. We've thrown all sorts of fuels at this engine, and it still magically is able to run. And the other nice thing is that we can retrofit it to meet newer Tier 4 standards. So they were imposed for on-road sources in about 2010, and they've been imposed on off-road sources starting last year with full implementation around 2018. This was the experimental setup. We had our engine, we mixed clean air, we had a dilution tunnel which essentially equilibrates the mixture. We then pass that mixture through an oxidation flow reactor where we simulate aging, and then we had a bunch of gas phase and particle phase instruments to measure both hydrocarbon emissions, oxygenated VOCs, and size, mass, and composition of particulate matter. Yes?
Just wanted to clarify if people aren't familiar with the oxidation flow reactor, because you're talking about two different terms. One being long photochemical times, but short residence time, and that might be confusing for people. So basically, the oxidant in there, such as OH or ozone, is at a higher level than the atmospheric atmosphere. So the number of reactions that can happen in that short residence time simulates hours of aging.
That's correct. Right. So
People might be confused with how that works.
Right. So it's essentially taking the atmosphere and fast forwarding it by almost 100x. So it's a lot of chemistry in a very short amount of time. So I thought I'd shamelessly advertise the place that I come from. This is the Powerhouse Energy Campus, which is a research facility a mile north of Colorado State University. And it hosts the Engines and Energy Conversion Lab, which is a 10,000 square foot facility where we have about 7 to 10 engine dynamometers, and we can do a lot of engine research ranging from combustion studies to fuel characterization. Anyways, these were some of the students and the postdocs and the researchers who were involved in this particular effort. The experimental matrix was very simple. We used two different fuels, diesel and then soy-based biodiesel. About 90% of the biodiesel sold in the United States comes from soy feedstock. Two loads, an idle load and a 50% load, and then two after-treatment options. One which was part of the engine called the EGR, which is the exhaust gas recirculation system. Essentially, it takes part of the exhaust and dumps it back into the engine cylinder to reduce cylinder temperatures and reduce NOx emissions. So it's sort of a control technology but built into the engine. And then another option where we had the EGR that was part of the engine, and a DOC and a DPF that stand for diesel oxidation catalyst, which removes carbon monoxide and unburned hydrocarbons, and a diesel particulate filter that removes particles. So we did a set of experiments and we did a bunch of repeats. So here are results from all the experiments that we did as part of that study. So I have two panels here, one that shows results at idle conditions, the other one that shows results at the 50% load condition. What I'm plotting on here is the organic aerosol as an emission factor, which is grams of organic aerosol produced per kg of fuel burnt, as a function of the photochemical age that we simulated in our flow reactor. We've got different colors for the fuels and then different symbols for the after-treatment system. So a couple of different trends. One is that you see all these curves increasing, suggesting that as we age, we produce more organic aerosol, which is essentially an indication of SOA production. We see that for the idle conditions that the numbers are larger in general than the load condition. That sort of makes sense. Idle conditions are typically inefficient combustion, whereas at load you're a lot more efficient. We also find that the POA values, which you can think about as the organic aerosol at zero OH days, is much smaller than the SOA. So SOA is much larger than the POA emissions. We also find that with the after-treatment system, which is these greens compared to these reds, is that you get a severe reduction in the primary emissions, both for the load and idle conditions. But what's interesting is that with the after-treatment option, which is this green, green and light green for both the fuels, with photochemistry, you essentially make up the same amount of SOA as you find without the after-treatment. What we hypothesize is that the catalyst temperatures are too low for the SOA precursors to be removed from the exhaust, and so they end up producing the same amount of SOA as with the no aftertreatment option. We can combine the SOA mass that we measured with the measurements of unburnt hydrocarbons and the fraction of that reacted to determine a mass yield. So you can think about this mass yield as a fraction of the unburnt hydrocarbons that reacted and a fraction of that that then went on and formed aerosol. And we plot that as a function of organic aerosol concentration. And they sort of all line up on a curve suggesting that the organic aerosol is semi-volatile. Higher the organic aerosol mass concentration, higher is the yield, potentially from there being a larger absorbing matrix to condense into. We then compared those results against SOA mass yields that I measured as a graduate student with just unburnt fuel, right? So we were doing experiments with diesel exhaust and we compared them to unburnt fuel. And we find that at high OA concentrations, the fuel looks similar to the exhaust. But at low OA concentrations, the exhaust has a much lower yield compared to the fuel. Now, if we assume that the fuel and exhaust are actually equivalent, what we hypothesized is that at low OA concentrations, the condensation sink or the equilibration time is small enough or low enough that the flow reactor is actually producing condensable material, but the residence time in the oxidation flow reactor is not large enough or is too short for the stuff to actually condense. And so what this is saying is that the accelerated chemistry that we try and simulate in the oxidation flow reactor essentially prevents the SOA that's formed from actually condensing, and you could underpredict SOA mass yields. So the takeaway there is that idle conditions or conditions where the catalyst temperatures are lower can produce substantial SOA. The fact to bear in mind here is that we had a retrofitted system, whereas usually when you have an after-treatment system, vehicle manufacturers typically recalibrate the engine. And so it's not an apples-to-apples comparison, but in developing countries, there's a lot of cases in which after-treatment devices are essentially retrofitted onto existing older engines. The other sort of takeaway is that oxidation flow reactors are a great tool to produce SOA and measure SOA yields, but they might not work if the condensation sinks are too low, or they would only work when the condensation sinks are large enough and need to be used very carefully. The second study that I want to talk about is looking at isocyanic acid and the potential emissions and photochemical production from diesel exhaust. So isocyanic acid is a highly toxic acidic gas. At neutral to alkaline pH, it's readily absorbed into the human body. It has a very high Henry's law constant. And it participates in what are called carbamylation reactions, where essentially if you have a protein inside your body, the isocyanic acid dissociates and this cyanate ion essentially squeezes itself on the tail end and essentially impairs the function of the protein. And that can have consequences on human health. Some work that Jim Roberts has done, where he's essentially looked at a bunch of literature, suggests that values greater than 1 ppb or exposure to more than 1 ppb could be toxic. Those are pretty small quantities. Just to give you a sense of how toxic it is, methyl isocyanate, which belongs to the same family as isocyanic acid, was accidentally released in Bhopal, which is somewhere, a place in central India, about 32 years ago now, or 31 years ago. And overnight, there were about 5,000 deaths associated with this accidental release. And in about a month, there were about 15,000 fatalities. And people in Bhopal have not been served justice, and there's been a lot of first and second generation effects associated with exposure to this fairly toxic pollutant. Now, people have previous work that has measured isocyanic acid in the atmosphere, has linked it to both natural and anthropogenic sources. This is work done by Jim Roberts, where they used a chemical ionization mass spectrometer and measured isocyanic acid that correlated nicely with carbon monoxide in the lab, and they also deployed this in the field in Boulder and Los Angeles, and suggested that what they were seeing was a result of either residential wood combustion or biomass burning. John Liggio's group at Environment Canada did something similar in the city center in Toronto, and found this nice correlation with benzene, which could potentially be from wildfire. The benzene could be from wildfire sources, but I think they did this in the summer, and there wasn't any residential wood combustion, so they tied it to anthropogenic sources or mobile sources in the city. So I'm going to sidestep a little and then come back to the sort of topic of isocyanic acid. So the emission standards for NOx in the United States for mobile sources, both on-road and off-road, have dropped significantly. So this figure here shows NOx and PM standards for a particular, for I guess, different types of engine sizes. And this is only for the off-road sector as a function of the years. So this is 96, 99. You see big bars or tall and wide bars. As you go to 2012, 2015, you see short and small bars, suggesting that the standards have really gone down with both NOx and PM. So there's been about a factor of 25 decrease over the past 20 years, which corresponds to a 60 or 70% decrease every 3 or 4 years. Now, some of this sort of meeting this strict standard has meant modifications to the engine in terms of adding exhaust gas recirculation systems, but at a certain point, that's not sufficient. And so engine manufacturers have typically employed what are called selective catalytic reduction systems. Essentially, what you do in such a system is you take ammonia, you thermally decompose it to give you ammonia, and then this ammonia can combine with both the NO and the NO2 to give you back nitrogen. The problem in the SCR chemistry, though, is that you end up producing isocyanic acid. Now, what's believed is that this isocyanic acid quickly hydrolyzes to give you ammonia back. But these systems have known to have ammonia slip, meaning when you have a transient duty cycle on a on-road vehicle, you can get excess ammonia out of the tailpipe, and that's just because you're injecting a lot more ammonia than you need. And so the next obvious question is, if you're getting ammonia slip, can you get isocyanic acid slip? And given that isocyanic acid is a fairly toxic pollutant, we need to be concerned. And Jim Roberts raised this fact, which motivated the study. So what we did was we retrofitted an engine to develop a configurable SCR system where we had complete control over the SCR system, and we measured isocyanic acid from both the primary emissions and the photochemical production of isocyanic acid, and then while it wasn't our explicit aim then, we've continued that study to look at air quality model predictions and possible ambient concentrations of isocyanic acid in a representative urban airshed. So this was the engine that we used. It's a 4.5 liter intercooled turbocharged diesel engine, something that you'd find on a tractor or maybe a small bus. It had a diesel oxidation catalyst that removes CO and hydrocarbons, DPF that removes particles. We designed a tank, a pump, and an injector system, and a mixing baffle system. Got ourselves donated a SCR catalyst because those can be quite expensive, and tried to measure isocyanic acid coming out of the tailpipe. And we did these tests at a bunch of different loads, did a few repeats, and for the heck of it, also looked at the influence of biodiesel. This was the setup. This is the engine. This is the main exhaust line that goes up, bends around here. This was the injector from which we injected urea. This was the urea tank. That was the pump. This was the catalyst It was a configurable system, so we could do anywhere between 1 and 3 catalysts. And this was our exhaust, and we had some sampling ports from which we measured the emissions. So when I say we had a configurable systematic setup, what we did essentially was vary the ammonia injection rate and measured the NOx in terms of the grams per kilowatt hour, and we also measured the isocyanic acid. And so for this particular test, where we start off with the NOx standard, which is in the tier 3 limits, as we add more ammonia, you reduce NOx. This is sort of the stoichiometric range. Even at about half of that stoichiometric range, we've met the tier 4 standard. What was surprising was that the isocyanic acid signal basically didn't change at all. We were so scared that we actually injected, what we did was we thought we were not measuring isocyanic acid correctly. So we actually, instead of measuring the isocyanic acid here, we measured it here, and then we saturated our instrument and lost 2 days because of that. So clearly the ammonia decomposition, the urea decomposition was producing isocyanic acid, but the isocyanic acid was being hydrolyzed in this catalyst to give you back ammonia. We repeated the test in hope for some isocyanic acid signal. In no cases did it increase, and in some cases it actually decreased. There was only one experiment where we actually saw an increase in isocyanic acid, suggesting that SCRs are not a source of isocyanic acid. We compared our measurements to some work that's been done, that has been done earlier. So this is all our data at the 3 different engine loads. We compared it to a study that we'd done a year ago without the DPF and DOC, and it's essentially the same, suggesting that the isocyanic acid is not being produced in the DPF or DOC, that it's coming directly from the engine. There's some agreement with the study from a Swiss group, but they do find a difference in no DPF or SCR and SCR, suggesting that the SCR is a contributor of isocyanic acid. But we think they might be biased in this particular measurement because they used an offline technique, whereas we used an online technique to measure HNCO. The results with the Wenzel study, this is John Liggio's group at Environment Canada, are a little confusing. We're not quite sure why we are so high compared to them, but it just might be because it's an older engine. This is a 2001 engine and an on-road engine that only had a DOC on it. We also compared it to light-duty HNCO from light-duty gasoline vehicles. Those were measurements made by Tim Bertram's group when he was at San Diego. And he thinks that the isocyanic acid is actually produced in the catalytic converter. These are results from a study that we did last year where we specifically looked at only the photochemical production of isocyanic acid. Essentially, we used a flow reactor. As we aged the diesel exhaust, we basically saw increases in isocyanic acid. It's fairly flat here, suggesting that nothing happens in, let's say, the first couple of hours, and then you get this dramatic increase. But we parameterized the isocyanic acid emissions, tied them to CO emissions, and then parameterized these curves purely numerically and put those in an air quality model, and made predictions for isocyanic acid concentrations in California. What we found is that you get hotspots over urban areas. So this is isocyanic acid in PPT, and we find that most of it seems to be coming from the primary emissions from diesel exhaust. Some of it comes from secondary processing, but biomass burning is a tiny sliver of the actual isocyanic acid that we measure. We compared it to measurements that Jim Roberts did as part of CalNex, and our sort of high estimate agrees fairly well, and it also agrees well with the Wenzel results, and that's how we think we have the right parameterizations and the right model capabilities here. But we don't think it's a big concern because the maximum concentrations that we find are about 100 ppt. And earlier effort has suggested that you need to be exposed to values larger than 1 ppb for it to be a concern. But in places where there's lots of diesel vehicles, like Beijing or New Delhi or Paris for that matter, where diesels are a lot more prominent, they might reach higher concentrations. So emissions controls are not a source of isocyanic acid. The industry would be thrilled to find that out. Diesels might be a dominant source, but it's probably not high enough to be a concern. Okay, moving on to the third study, where we employed an air quality model to look at the source and precursor contributions to organic aerosol in urban air sheds. So there's been a growing controversy / debate about what the largest source of organic aerosol in urban air sheds is. People have looked at weekday versus weekend effects, looked at organic aerosol mass and OA to CO ratios, looked at the composition and the radiocarbon content, and suggested that it's gasoline use, not diesel use, that contributes to most of the organic aerosol in places like Los Angeles. And there's some box modeling effort that suggests the same. Alan Goldstein's group did a detailed speciation of the components in the gasoline and diesel fuel, and based on that and some ambient measurements, concluded that there were too many important SOA precursors in diesel fuel, and therefore diesel fuel is probably the reason diesel fuel is the reason for organic aerosol concentrations in the Los Angeles basin. And then there's sort of this third angle where Joey Ensberg from John Seinfeld's group said that, mobile sources, we can only explain the observational data if mobile sources are an extremely small source, or if we've completely botched the laboratory-based experiment. So the fair bit of uncertainty and debate going on between the contribution of gas versus diesel in urban areas. What's been missing is a bottom-up study using a chemical transport model where you can account for emissions and chemistry and transport and deposition that incorporates new laboratory findings and then determines what the source contribution is. So we've done exactly that. We've done that with the latest and greatest version of CMAC for the time period of May and June 2010, which coincided with Calnex at 4 kilometers, drove the meteorology using WRF, standard set of emissions inputs, initial and boundary conditions, and the standard suite of the gas phase chemical mechanism and the aerosol module. The organic aerosol module included a 4-bin volatility basis set model that Environ developed for the EPA through a contract where we treat the POA as being semi-volatile and reactive. We include SOA from both VOCs, so these are aromatics and smaller alkanes, and also IVOCs, which are typically constituted of larger, higher molecular weight, larger than a C12 linear branched and cyclic alkanes. And then we also include an aging scheme that in my opinion is a little antiquated. We performed a bunch of simulations. We did a traditional model where we consider the PO as non-volatile and don't include IVOC, and then have 2 VBS versions, one that has an unconstrained version of IVOC that's determined as a scaling based on POA emissions, and then one that's source specific. So the IVOC emissions from gas, diesel, and biomass burning are based on specific laboratory studies. So here are predictions from the updated model, where we compare the predictions to daily average measurements made at the chemical speciation network sites. And in the Los Angeles basin, we're actually only underpredicting by maybe 30 or 50%. But when we compare against the AMS data that were measured at the Pasadena ground site, we significantly underpredict. And we're not quite sure why that is. We've talked with Jose about it. We've talked with a bunch of modelers about it, and there's lots of hypotheses being made that maybe the model resolution, even at 4 kilometers, is too large to capture the Pasadena ground site. That the Pasadena ground site was actually very close to the 405 and whatever the other interstate highway was, that the WRF doesn't capture the meteorology that splits the airstream between Los Angeles and between Pasadena and Riverside well enough. And so we don't know what the reason for good agreement with CSN or decent agreement with CSN, but under prediction versus the AMS is. So we compare our VBS IVOC model with the traditional model against the AMS measurements, but on a fractional basis, because we're not getting the absolute concentrations right. And it seems like the gasoline and diesel contribution through this blue and red colors seems to mirror the HOA fraction. The cooking organic aerosol is slightly over predicted, but we get the POA SOA splits and the source contributions roughly right, definitely much better than the traditional model that thinks it's all POA. And for the first time, we've been able to make comparisons of the IVOC measurements that were made by Alan Robinson's group and compared them to the predictions that we measured. And the primary IVOCs compare well with the mobile source IVOCs, and these oxygenated compounds compare well with these other sources. So there's some confidence in having developed the right emissions for the IVOCs and the right reaction rates and potentially the right contributions to SOA. Next we look at the model predictions for the organic aerosol from the gasoline and diesel sources. This is what the VBS with the unconstrained IVOC and then the VBS with the constrained IVOC suggests. Basically, this says that the gasoline bar is much taller than the diesel bar. It doesn't really matter if we scale up the IVOC emissions. Gasoline sources always seem to be much larger than diesel, about a factor of I'd say 10 to 15 in the Los Angeles basin, and it's the same. This is a domain-wide cumulative distribution function suggesting that the gasoline contribution to organic aerosol is about 35 or so %, with the remainder coming from all of these other sources: wildfires, biomass burning, stationary sources, dust, road dust, and things like that. So the takeaway there is that IVOCs are an important source of SOA, and that gasoline-powered sources are likely the most important source of organic aerosol and the single most important source in urban areas. So some implications from the three case studies that I've presented. Mobile sources are very important sources of pollution, although the secondary PM contribution is still uncertain, needs to be studied some more. New diesels that have DOCs and DPFs and SCRs and AOCs and all these sorts of short-formed after-treatment devices are probably quite clean if they work, right? And if their parents haven't set them to be turned off, but retrofitted diesel engines might have some issues. Diesels, the engine itself, the chemistry in the cylinder seems to produce isocyanic acid from some crazy reactive nitrogen chemistry inside the combustion cylinder, but it's unknown what that production pathway is. And we have a few hypotheses, and we'll test that over the next year or so. Some ongoing work. We're trying to model the SOA that we measured using a semi-explicit model, particularly trying to look at the influence of IVOCs and thinking about how to model oxidation flow reactors where you cannot assume equilibrium partitioning and you have to assume kinetic gas particle partitioning. I have another master's student who's finishing up where we've used neural networks to try and model fuel economy and emissions from various types of hybrid vehicles, both electric hybrids and hydraulic hybrids. With the electric hybrid, when you brake, you essentially charge the battery. With the hydraulic hybrid, when you brake, the regenerative energy is stored in an accumulator as a hydraulic fluid, and then when you want to accelerate, that hydraulic fluid depressurizes and gives you very strong acceleration. It's a company in Loveland, Lightning Hybrids. that's invested in that technology, and that gives you about a 30% improvement in fuel economy and significantly reduces emissions reductions. We also have another PhD student who's working on air quality modeling of organic aerosol in the South Coast Air Basin. That's where, South Coast Air Basin is a nice test platform to test all sorts of crazy ideas, and we're trying to do that to look at the influence of vapor wall losses on IVOCs and aging and things like that. And we recently, as we speak, finished a study up in Missoula, Montana, where we deployed our portable temperature and relative humidity controlled smog chamber, and you can see that here. We had to color it blue because the director of my energy institute didn't like the plywood on the outside, and so I made him buy the paint. But this is the fire lab for those folks who haven't been there. This is a pallet where they set the thing on fire. They pressurize this entire chamber so that the only way the smoke can escape is through the stack. This is about 5 feet wide. There's a platform about 50 feet from this, from the floor here, where we sample. This is that sampling line that bends around, comes over here, and we use a ejected diluter system to add into the chamber. And here's some pretty cool graphics of one of the fires that we simulated, and one of my PhD students sort of leading that effort. Okay, with that, I can thank you for listening to my talk, and I can take any questions. Yes.
I have two questions. One is Fresno looked a lot like Pasadena in your class.
Fresno looked a lot like Pasadena.
And I wonder, whether you could learn something from what they have in common.
For the isocyanic acid stuff?
No, for the aerosol predictors.
Oh, okay. Fresno looked a lot like Pasadena. That's right. Yeah, so we get better comparison in the basin, but we get poor performance in the Central Valley. But Pasadena probably has a very different mix of sources compared to the Central Valley, which is a lot more dominated by agricultural and maybe oil and gas sources. Whereas Pasadena, you would expect it to be mostly sort of mobile source type of environment, maybe with a small influence of the biogenics, which are in the mountains right to the northeast of Pasadena.
And Fresno might have that.
Yes, biogenics. Yes.
You think it's dairies and whatnot, but it might not be. But that's just something.
Yeah, that's an interesting thought. The other problem that with this data set is when Jose's group compares their AMS measurement to co-located filter measurements that EPA, UNC, and Rodney Weber's group at Georgia Tech did, the AMS measurements are higher compared to the filter measurements. But he explains those away by saying that the artifact correction that the other groups used for the filter measurements were too high. So,
and then your flow reactor with respect to measuring aerosol production.
yes.
Since you're doing this with relatively high concentrations and high oxidation rate, whereas in the real world you would expect stuff to dilute a lot more quickly.
Yes.
So could there be a nonlinearity because of the high concentration of your aerosol constituents?
Absolutely. Absolutely.
How do you deal with that?
Right. So the goal of our study was to try and assess the potential without any regard, or with little regard to the atmospheric relevance. And so our goal was to try and oxidize everything that came out of the diesel exhaust and to look at the enhancement in the organic aerosol. And we've done that, and we've calculated SOA mass yields. Now, for some reason, the mass yields that we calculate seemed, at least at these high concentrations, seem to agree with the unburnt fuel experiments that were done in chamber experiments that were atmospherically relevant. So there's sort of an indirect connection where, because we're getting the same mass yields as in a chamber experiment, maybe the chemistry that we've simulated in the flow reactor is not that different than that in the chamber experiment. Now, it's possible that the chamber experiment is not atmospherically relevant, but at least that's sort of the paradigm with which most atmospheric chemists use environmental chambers. So that's sort of one piece of evidence. The other is that we've looked at mass spectra from the AMS, from our flow reactor experiments, and compared the factors, or the positive matrix factorization factors, against PMF factors from diesel exhaust experiments done on chamber experiments. And those seem to correlate really well as well. Now, I don't know enough about aerosol mass spectrometers, but some people have argued that the AMS is too blunt a tool to really say that if two things look similar, they must be similar in their bulk composition. But that's another piece of evidence where we can say that the flow reactors are probably similar to chambers. But that's a great critique, and I think everyone who's using a flow reactor is sort of thinking about that issue. Yes?
Well, there are a couple of things about the flow reactors avoiding. One of them is that while there's OH is maybe 1,000 times higher than the ambient, the dose is 0 or minimum. While the atmosphere, they're often comparable. And so OH reactions predominantly, not always, but predominantly would tend to functionalize and grow aerosol mass, while photolysis predominantly, not always, fragment and reduce. So that's one issue, but I guess there is no good answer to that.
Right. So
the other issue that I have, though, is a technical question. How do you do residence time? Are you sure it's flood flow or parabolic flow? Is it a single residence time, or do you have distribution, parabolic distribution of residence times?
Right. So let me answer the first question. So typically, what people who have used flow reactors have seen is that you start off with some organic aerosol concentration, you get an increase, and at some point you start getting a decrease. Typically, that decrease has been attributed to either the OH chewing on the particles themselves, and the particle reaction with the OH fragmenting the molecules, or the gas phase molecules fragmenting, and then the organic aerosol then evaporates because the absorbing there's no vapor phase to keep it in equilibrium. But no one has looked at the influence of photolysis in these flow reactor experiments, or the lack of photolysis in these flow reactor experiments, and how they would be sort of in the real world. And I don't know how we would do these experiments. I mean, there are some flow reactor experiments that have been done directly on ambient air. Maybe if you had a chamber co-located with that flow reactor, and you could compare the chamber versus the flow reactor, you could maybe say something about the influence of photolysis. The answer to the second question is yes, it's a distribution. It's not a plug flow. And there have been the flow reactor that we got was from Bill Bruin. There have been some studies to show what the actual distribution of the residence time is. We essentially assume the median value of the residence time when we present all our data. So half the stuff has had more time to react with OH, half the stuff has had less time to react with OH, but essentially it would be a error bar on our data. There have been at the American Association for Aerosol Research Conference this year, there were at least 6 new designs of oxidation flow reactors where they have resolved issues with the residence time. Let's see. Where they have come up with, so in this case, this was the inlet, they have come up with diffusing cones at the inlet to avoid eddies in these corners right here. So I think we are just starting to use the flow reactor as a tool. We're probably using it incorrectly, but we'll probably start using it much better in the future. Yes.
So should we trust the program?
I think the results from this study and the results from some of the other studies, and some of this is starting to coming out in the literature, shouldn't discount it. There's a lot more to do with regards to the design of the flow reactor. Bill Brune has licensed the flow reactor, if you can call it, to Aerodyne Research, and they're going to develop a commercial version, which will probably be a lot better characterized. So I would say we don't want to discount it, mostly because the experiments are so easy to do. I mean, I could go tomorrow and do redo these experiments in a couple of days. If I had to do these with a chamber, it would be a lot more painful. And so the ease of use demands that we invest more resources into making this design better. Some of the initial evidence suggests that we are reproducing somewhat the same chemistry as the chamber, if not the atmosphere. But again, there's lots of other issues as well.
Follow-up. I mean, how much could it be that diesel exhaust might have a slight variation in composition with other fuels, so you have more oxygen compounds? Does that play any role in the discrepancy there?
It could possibly. I would like to think that the exhaust at idle conditions is probably very close to the unburnt fuel, just because the fuel essentially moves through the engine cylinder, is vaporized, and some fraction of it makes it out. As to if the speciation of the exhaust is the same between the fuel and the exhaust, maybe not, but maybe the SOA precursors and the composition of the SOA precursor is close enough. So the total VOC speciation might be off, but maybe the SOA precursor composition is similar enough that they can be treated to be similar. Yes.
One other question. So I was actually intrigued by your genome study, so to look at the proportions of gasoline. So did you do anything with the NEI emissions, or did you just plot the situation for this that the activity that is correct? Because we found that the emissions were very terrible.
Right. So the NEI, I would like to second that they are terrible. We are having we've had issues with even good model measurement comparisons with things like carbon monoxide. And so there are definitely issues with the inventory. The things that we did tweak to get the gasoline and diesel is we took the total so we developed new VOC speciation for both gasoline and diesel sources based on Andrew May's papers in ES&T, atmospheric environment, and JGR for gas, diesel, and biomass burning. So we developed new speciation profiles. We determined IVOCs not as a scaling on the POA, rather we determined them as a fraction of the total hydrocarbon emissions. And so we're not sensitive to the fact that POA, the emission factor for POA can change as a function of the gas particle partitioning. And then we use the volatility distributions, again from Andy May's paper, but that was separate for gasoline, diesel. And so we've tried to incorporate the latest findings about organic aerosol, at least from gasoline, diesel, and biomass burning. And we think the methodology is robust, but as to whether the total VOC emissions are right, we don't know yet. I mean, sort of the studies that will come out in the future will hopefully improve that inventory. More questions?
Just a quick question.
Yes.
Chemically, are biodiesel and traditional diesel the same blockchain hydrocarbon molecules?
Yeah, I mean, they're not. I mean, they're incredibly different. So for diesels, you typically get two peaks. The fuel sort of spans somewhere between a C8 to a C22 for diesel, and it's a very broad distribution with two peaks, one peak for single ring aromatics at the C6, C7, and C8, and then you see another peak at C15 or C16. So that's for diesel. When you look at biodiesel, about 3/4 of biodiesel is essentially made of two molecules, somewhere between a C16 and a C18 ester. So it's essentially just 2 or 3 molecules. So they're incredibly different in terms of their fuel composition. But when we look at primary emissions of organic aerosol and secondary organic aerosol production, they're nearly indistinguishable. So we don't know what our best hypothesis is that these two biodiesel molecules essentially fragment and give you that same distribution as diesels. But not the aromatics. And so maybe the aromatics are sort of in the, it doesn't matter if you have a few more C15s as compared to a C7 or a C8, because in terms of their SOI mass yields, they're identical. Okay, thank you very much for your attention.